Thank you for being here for the very last talk of today. I'll try to be quick in 15 minutes. So I'd like to talk about robot action planning in unknown and uncertain environments. In some ways, we can classify planning approaches in terms of how much is need to be known about the task environments. If object models are known, locations are known, uncertainty models are known, then we can do offline planning, right? We can take our time to plan a good motion path, for example, for a robot to execute. But if object locations are uncertain, then we also need online planning adjustment based on perception. But in an entirely unknown environments, then we need online planning based on perception that is necessary. So this is the focus of my talk today. I'd like to talk about some recent progress in my group. And let's consider this problem of visual coverage of unknown structure like a nuclear facility that is hazardous for people to enter, and we need an autonomous robot to map, to have a complete visual coverage of this, get images so we can do 3D reconstruction to facilitate later inspection tasks. And this is a very large and complex environment, and we need a robot with limited resources to do all kinds of things: perception, mapping, planning, motion execution. And what can be the approach? Our experience requires a good representation of the object, of the information explored and gathered. And we know that occupancy grid or voxel map is a natural representation for gathering visual information, but that's too low level. So our approach here by my former student is to build upon that a very effective called active perception network to reduce space, to have much more information content with a much small physical space to hold that content, and you use algorithms to maintain this so-called APN. As the robot explores the environment, the APN needs to be grown, but at the same time pruned. So the nodes and the connections that are redundant need to be pruned to make it efficient. And with that, we are able to use any graph-based planner for a tour planning, like traveling salesperson's planning, and all in real time at the same time for efficient coverage of large structures. So the key here is representation, adaptation of the planning to the found information. And in this example, so we can have a UAV, starts with knowing nothing, and this is simulation, but it has a field of view as in this cone shape, and started to explore the environment and build this perception network, at the same time doing this tour planning. So as you can see, there's some colored regions. These are the clusters of a lower level perception network. So all the nodes are within some distance threshold, and they can be reachable by the robot. And so planning can be done by a next best view local planning in clusters, and global clustered sequence planning to cover the entire building as robot explores and plan at the same time. So this can actually really complete the coverage as long as no frontiers can be found anymore. So the robot goes back to its original starting location. And with this representation and planning, graph-based planning, we can greatly reduce the space growth and time for planning. The time for planning is almost constant in milliseconds for each cycle, and the space, even though voxel grows very fast, the actual APN nodes and edges grow much more slowly. That achieved the scalability for different environments, even very large ones like the warehouse, or 90 meter by 30 meter in area, and can be done very efficiently in just a few minutes. Now, I want to also talk about, in this kind of unknown environment, what about finding some semantic objects, autonomously search for semantic objects? That requires a lot of capabilities that we have related research, from active SLAM to next best view and deep learning to map what's discovered in an environment to the robot action and POMDP. We just heard POMDP from Hannah earlier. That's explicitly planning with uncertainty models to cover all kinds of inaccuracies. This is great. All these capabilities are important, but as you can see, they're not enough for achieving this task. There are still gaps. So we propose to fill all the gaps, so enable this kind of autonomous search of semantic objects in unknown environment. And the most important thing here is a synergy to connect semantic SLAM, for example, and probabilistic planning under uncertainty, like POMDP, to do automatic and in simultaneous planner adaptation. So we not only do planning in real time, we adapt the planner models in real time to leverage the semantic SLAM information or achievements, results, to reduce uncertainty. And that makes it much more accurate in motion, and use semantics prior to also relate objects seen but may not be the target objects to the target objects who exploit their functional relationship to increase planning efficiency. Now, I'd like to talk about my favorite subject, online planning, execution, robotic assembly. Again, we heard about robotic assembly, assembly sequence planning, and assembly planning from Dan earlier. So the challenge is tight tolerance versus great uncertainty effect and varied part geometry and complex context state to complicate the situation. And we know existing approaches are either for very simple cases or using learning-based approaches for task-specific solutions. The question is, can we have a general efficient solution? So our experience shows that we need geometry invariant contact representation, general learning, to catch uncertainty effect, and kind of skill learning, and constraint search with compliant motion. So geometry invariant sphere tree representation is very effective to unifying the expression of contact constraints. You can have very complicated geometry of objects and contact situations, but we can consider each contact constraint as between two spheres, and that greatly simplifies the computation of contact configurations. But that's not enough because it's not accurate. And we also have sensing uncertainty and so on. So we try to use general learning. We call general because it's not task-specific, to overcome uncertainty effects. In this case, we try to map force torque sensing data to contact configurations and just to capture all the effects. And we do that automatically with automatic data collection and training. But the result is many-to-many mapping, and it still doesn't give us the most likely contact configuration. So we also do constrained search to find the most possible contact configuration. And these combinations allows us to do rather complex assembly, such as in this case, a gear set assembly. The geometry is pretty complicated with all these teeth, and the clearance is pretty small, but our approach can be robust to uncertainty 10 times of task tolerance. And you can see multiple contact situation happens, and other parts may even move, and we need to make sure the gear meshes very well. This is all actual speed, so it's very efficient in this case. And we further leverage this for more general assembly, not just a single insertion, multiple insertions. So we consider a dense packing situation. If we have objects that we don't know, we can quickly use, say, RGBD perception to build object model, object pose, which can be rough and imprecise, but we're not afraid because we can handle uncertainties. And we can do dense packing planning, that's some form of assembly planning, to maximize the space of a container by putting objects into it and optimize the motion path. And then execute it with our robust insertion strategy. And this is an example for that. So we have these objects the robot has no knowledge about, and it does a packing planning to fit the container with the best possible way, maximize space utilization, and also the motion path planning. When it encounters some contact and our contact prediction strategy works, and object insertion can be successful. So I'm going to, I don't know how to I tried to fast forward it, but you can believe me that it finishes it nicely. And now just recently, we also applied this to deformable objects like bags of tissues for packing. As you can see, we can quickly have a segmentation of different bags and pick up the bags. And now you look at the third bag. When we try to enter this into this container, you can see contact happened. But this is predicted and we correct it. So in that sense, we are trying to consider planning problem as detecting some spatial relationship among objects and robot or contact situations, and to correct undesired spatial contact situations to a desired one. That's to accomplish this kind of contact-rich assembly. Finally, I just want to use 2 minutes to talk about the same strategy using spatial relationships among objects to do deformable manipulation. In this case, we don't know the object model. We just use the RGBD camera to detect the spatial relation. So the key here is perception to perceive spatial relations, and based on spatial relations, we try to do a transition to the desired spatial relation. And this is inherently robust to uncertainty, right? Because any kind of situation can happen as long as we detect it, we'll try to make a transition to a desired situation. And finally, this is a more recent work. This is not a linear deformable object, but a two-dimensional deformable object. The same approach works. Try to finish this, I don't know, this is what is called, this is a scarf tying problem. So, yeah, once you're given a task, you have some desired states, desired stages of spatial relationships to achieve. And we populate some neighboring spatial relationships because of uncertainties and inaccuracy. And then planning is simply try to make transitions from one spatial relationship to another. And that's my talk. So the takeaway is shown there. Thank you very much.
Thank you, thank you. Questions? So maybe I can echo one of the questions we heard earlier in the session. In these kinds of settings where the robot is learning or perceiving how to interact with objects, there's always a safety question to make sure you don't break things along the way, right? So can you comment a little on how that fits in with how you're approaching these things?
Yeah, force torque sensing is great. Then we can have guarded move, right? While we make a contact, we make sure we are not slamming the robot or some objects into another. So compliant motion is also trying to be safe. So these are all very important capabilities. And we try to combine all these capabilities.
Okay, okay. Time for maybe one more question here.
I think it's too late. It's already.
Okay, well, let's say thanks again to Professor Xiao and to all of our speakers.